Assalamualaikum and good day to examiner, supervisor, lecturer and everyone. My name is Muhammad Firhat Kimi bin Mazli and my student ID is 2024649708. Today, I will present my final year project and the title is Machine Learning Based Intrusion Detection System for Network Security, and the system developed for this project is named AI Sentry. And this project was completed under the supervision of Dr. Muhammad Yusuf bin Darus. The purpose of this project is to develop an intrusion detection system that use machine learning to classify network traffic as normal or malicious. Okay, now we go to the presentation flow. Okay, for the presentation, I will begin with the research background and the problem found in the traditional intrusion detection system. After that, I will explain the proposed system design, the methodology, dataset preprocessing, model development, and the AI-centric dashboard. Then I will present the model result, discuss the important finding and end of the project limitation, recommendation and conclusion. The main storyline of this project starts from the cybersecurity problem, continue with the leakage-free machine learning pipeline, and ends with the working intrusion detection system dashboard. And now we go to the research background. Okay, nowadays, many activity depends on computer networks and the internet. So this include banking, communication, education, business, and entertainment. Because of these services are connected to the network, the opportunity for cyber attacks also increases. Attackers are continually changing their technique to avoid security system. Traditional intrusion detection system normally depends on fixed rules or attack signature. This means they are effective for attack that are already known, but they may fail when an attack is new or slightly modified. So machine learning provide another approach. Instead of only comparing traffic with known signature, it learns pattern from historical network traffic. Based on this pattern, the model can predict whenever new traffic appear normal or malicious. In AI Sentry, the user upload the network traffic file. The system analyze the flow pattern, produce a prediction, and display the result through the dashboard. Now we go to the problem statement and project objective. There are 4 main problems identified in this project. Okay, the first problem is that new or modified attack can be bypassed signature-based intrusion detection system because there may be no matching signature in the database. The second problem is the high number of false positive. Sometimes normal traffic is wrongly detected as an attack. Too many false alerts can make security administrator ignore important warnings. The attack problem is a large amount of network traffic. Monitoring every connection manually is difficult and not practical. And last problem is that traditional system require continuous signature update to detect new threats. Okay, based on this problem, the first objective to develop a machine learning based intrusion detection system. Okay, the second objective is to train and compare several machine learning algorithms. The third objective is to build an interactive dashboard for scanning uploaded traffic. And the final objective is to improve model performance using feature selection, scaling, and class balancing method. Okay, now we go through the project scope and the dataset. Okay, the dataset used in this project is CICIDS 2017. The dataset contains label network flow representing binning traffic and several attack categories. Example include DDoS, proc scan, denial of service attack, web attacks, bot attack, and brute force attacks. Originally, the dataset contains 78 statistical network traffic feature. This include flow duration, forward and backward packet length, packet inter arrival time, flow bypass per second, packet rate, and TCP flag count. The input for the AI Sentry dashboard must follow the CICIDS feature structure because the model were trained using this feature. The current system can only perform detection. It's not automatically block traffic or take action against the attacker. Testing was also performed in controlled environment instead of real organization network. Real-time packet capture can be added in future development. Okay, now we go through the literature review. Okay, based on the literature review, machine learning can achieve strong performance for intrusion detection. However, several important problems are still found in the previous studies. The first issue is the detection limitation. Traditional signature system cannot easily detect zero-day or modified attacks. Machine learning models can also perform poorly when minority attacks classes are not properly represented. The second issue is false positive. A high number of false positive can overwhelm administrators and reduce their trust in the system. The third issue is dataset quality. Older dataset may not represent modern network traffic. Even newer dataset can contain duplicated or incorrect records, which may produce misleading accuracy. The fourth issue is class imbalance. Binning traffic usually has more record compared with the attack categories. Because of this, a model may achieve higher overall accuracy but still fail to detect rare attacks. So AI Sentry respond to this gap by removing duplicate records, splitting the data before fitting any preprocessing tools, comparing 10 models, and focusing on F1 score and recall instead of accuracy only. Feature selection train only smooth, and consensus voting are also used to improve the reliability of the system. Then we go to the proposed system overview. This slide show the input, process, output structure of AI Sentry. For the input, the system receives CSV file containing network flow data. During the process stage, the system clean data, select the required feature, apply the safe scaler, and send the traffic to the trained machine learning models. Each model predict whenever the network flow is normal or malicious. These predictions are combined using consensus voting. Okay, for the output, the dashboard display the final scan verdict, attack rate, confidence, model comparison, threat level, and list of suspicious traffic flows. The main system component are the user dataset, machine learning engine, train model dataset, and the dashboard interface. And now we go to the methodology. Okay, this project use a hybrid methodology that combine software development life cycle with a machine learning research activity. The hybrid method is useful because machine learning development is not always a straight process. When a problem is found, such as data leakage, I can return to the earlier stage, correct the pipeline, and train the model again. Now we go to the data preprocessing pipeline. Data preprocessing is one of the most important part of this project because the quality of the data directly affect the model result. First, all CI, CIDS, CSV files are loaded and combined. Next, extra spaces in the column name are removed. Broken special character in some web attack label are also replaced with normal characters so the familiar attack label are not separated incorrectly. Infinite value are replaced and row containing missed value are removed. Column with no variation are also dropped because they are not provide useful information to the model. After that, duplicate networks are also removed. Most importantly, the dataset is divided into training and testing set before the scalar or feature selector is fitted. This prevents information from the test set from entering the training process. The test set must remain completely unseen so that can give an honest evaluation. The first version of the pipeline produced around 99.99% accuracy, but the result was misleading. After correcting the leakage, the performance become more realistic and trustworthy. Now we go to feature selection, scaling, and class balancing. After cleaning the dataset, feature selection is performed using select KBase with mutual information. The original dataset contains 78 flow features. Select KBase rank the features based on their relationship with the target labels, and the only 45 most informative features are selected. This reduces unnecessary information, lowering the training time, and allow the model to focus on the most useful network characteristic. Next, robust scaler is used. Robust scaler use the median and interquartile range, so it is less affected by very large or unusual network flow values. And then we go to this project also use smooth to handle class imbalance. Smooth creates synthetic sample for minority attack classes. However, it is applied only to the training data. For model that support it, balanced class weight are also used. This give a stronger penalty when the model incorrectly classify minority attacks. The testing data is not imbalanced or modified. The testing data is not balanced or modified. This is important because it must represent the original data distribution. And then we go to the model development. 10 machine learning algorithms were trained and compared in this project. The tree and ensemble project are random forest, decision tree, and gradient boosting. The boosting model are XGBoost and Light GBM. The classical machine learning model are support vector machine, K nearest neighbor, logistic regression, and naive bias. The final model is multi-layer neural network with hidden layer containing 256, 128, 64, and 32 neurons. Using several models allowed me to compare different machine learning approach instead of depending on only one algorithms. After training, every model is saved as a PKL file using job lead. When the flash server starts, the model are loaded directly, so there are not need to train again each time the dashboard is open. SVN and KNN were limited during full file scanning because they are required more processing time and large data set. Then we go through the data leakage finding. Okay, one of the most important finding in this project was data leakage problem. In the first pipeline, near identical network flow could appear in both training and testing set because the dataset was randomly divided without removing the duplicate flow properly. The scalar and feature selector were also fitted before the train test split. This allow information from the testing data to influence the training process. Because of this, the model report approximately 99.99% accuracy. However, the model was tested using actual port scan sample. It failed to detect them correctly. To solve the problem, duplicate flow were removed based on the feature columns. The dataset was then split before any fitting was performed. Select cables and robot scaler were fitted only using the training data and were later applied to the testing data. After making this correction, port scan recall increased to approximately 99.99%. 99.9%. This shows that very high accuracy number does not automatically mean that the model is good. The evaluation pipeline must also be clean and trustworthy. Now we go through the dashboard and consensus voting. After training, the model were deployed through an interactive flash dashboard. The dashboard contains several pages, including dashboard overview, ML scanner, traffic analysis, scan history, detection, dataset, report, and model. During scanning, the user uploads CSV file. The uploaded data goes through the same cleaning, feature selection, and scaling process that were used during training. So, an AI scientist then use assemble consensus voting. Value eligible full scan model produces its own prediction. And network flow is only classified as malicious when a strict majority of the model is agree. One or two model predicting an attack are not enough to produce a final malicious verdict. The threat level is classified as critical, high, medium, or low based on the number of model agreeing and their average confidence. The final output include the attack rate, confidence level, flag flows, verdict, and model by model comparison. Now we go through the model performance comparison. This slide present the F1 score and all 10 model after apply the corrected leakage-free pipeline. Random Forest achieved the highest F1 score at 99.67%. The decision tree achieved 99.57%, followed by Light GBM at 99.44%, XGPO at 99.38%, and Gradient Boosting at 99.15%. KNN achieved 98.8%, while the Neural Network achieved 98.01%. The lower performing models were SVM at 78.26%, Logistic Regression at 74.62%, and Knife Wire at 30.55%. Random Forest was selected as the best model because it achieved an accuracy of 99.89%, precision of 99.57%, recall of 99.78%, and F1 score of 99.67%. This means that Random Forest produced the best balance between detecting attack and avoiding incorrect attack predictions. Okay, now we go through the attack recall and cross-validation. Overall, accuracy is not enough to evaluate an intrusion detection system because the dataset is imbalanced. A model can achieve high accuracy by predicting the majority traffic correctly, while failing to detect some minority attacks. Because of this, recall were evaluated separately for each attack category. The results show strong recall for attack types such as DDoS, port scan, different denial of service variants, and brute force attacks. The best model were also evaluated using stratified 5-fold cross-validation. The training data was divided into 5-fold while maintaining a similar class distribution in each fold. The model was trained using 4-fold and testing using the remaining fold. This process was repeated 5 times. Cross-validation helped confirm that the model performed is stable and not only caused by one lucky train test split. So the main focus of this evaluation is honest attack detection instead of producing only high-looking accuracy value. Okay, now result display. Now we go to the result display in the dashboard. This slide show how the results are presented to the administrator. The model comparison, the model comparison table display the performance and prediction of each machine learning model. It include information such as accuracy, F1 score, number of attack flag, and attack rates. The flag flow tables provide more detailed information for suspicious attack records. For each flag flow, the administrator can see the number of models that agree, the average confidence, and the assigned threat level. The attack analysis page also present a chart showing the attack distribution and the behavior of the uploaded network traffic. This makes the result easier to understand compared with only displaying raw prediction value inside the Python terminal. And now we go to the discussing of the finding. From the result, tree-based and boosting model achieve the strongest performance. This model can handle non-linear relationship between normal and malicious network traffic. For example, an attack may be identified through a combination of packet length, duration, TCP flag, packet rates, and inter-arrival time. The relationship between these features may be too complex for a simple linear model. Random Forest also combines many decision tree. Each tree learn a slightly different part of the data, and the final prediction is based on the combined decision. This helps reduce overfitting and improve stability. Naive Bayes achieved the weakest result because it assumed that the input features are independent. However, many CICIDS 2017 features are connected. For example, packet count, packet length, flow duration, and byte per second can be strongly related. So naive Bayes also flagged too much binding traffic as malicious, which reduced its precision and F1 score. The main lesson is that correct preprocessing and evaluation are just as important as selecting powerful algorithms. Now, we go to the limitation and feature recommendation. Although AI Sentry work as a prototype, it still have a several limitation. The first limitation is that the system only support on-demand CSV scanning. It does not capture live network packet. The second limitation is that the upload file must follow the CICIDS 2017 feature schema. The system was also tested only in the control environment, not in the real organization. And the current output is binary classification. It identifies traffic as a normal or malicious, but does not provide exact attack name for every prediction. The system also does not automatically block malicious connections. For feature works, CIC float meter can be integrated to generate live network flow feature. Additional datasets such as UNSW NB15 can be added to the test whenever the model can perform well on different network environments. The system can also be extended to multi-class attack classification, where it identifies the specific attack categories. Other feature improvement include LSTM, auto encoders, user account, email or messaging alerts, automatic response, and real-time monitoring. Now, we go to conclusion. Okay, in conclusion, AI Sentry successfully demonstrate a machine learning based intrusion detection system for classifying uploaded network traffic as normal or malicious. The project showed that machine learning can improve intrusion detection. However, model accuracy alone is not enough. The quality of pre-processing, trend split separation, balancing method, and evaluation process must also be reliable. So that's all. That's conclude my presentation. Thank you for listening, and that's all for me. Thank you.